This is part 11 of a series on generative adversarial networks. In this video, we will look at the dual discriminator generative adversarial networks, shortly D2GAN. This video was produced in Korean and then translated into English. The audio was generated via AI, text-to-speech. First, let's look at the structure of the D2GAN model presented in the paper, Dual Discriminator Generative Adversarial Nets. Next, we will cover the formal theoretical analysis of the D2GAN model. And let's look at the role of alpha and beta, the hyperparameters introduced by the authors of the paper. Finally, let's implement a D2GAN model using Keras. D2GAN was introduced in 2017 by D2GAN et al. In their paper, Dual Discriminator Generative Adversarial Nets. Let's read a few sentences from the abstract. We propose in this paper a novel approach to tackle the problem of mode collapse encountered in generative adversarial network, GAN. Our idea is intuitive but proven to be very effective, especially in addressing some key limitations of GAN. We term our method Dual Discriminator Generative Adversarial Nets, D2GAN, which, unlike GAN, has two discriminators and a generator. We conduct extensive experiments on synthetic and real-world large-scale datasets. The experimental results demonstrate the competitive and superior performance of our approach in generating good quality and diverse samples over baselines. Now, let's take a closer look at the structure of D2GAN. D2GAN is formulated as a three-player game that consists of two different discriminators, D1 and D2, and one generator G. This allows it to solve the mode collapse problem of standard GANs. Given a sample X in data space, D1 of X rewards a high score if X is drawn from the data distribution P data, and gives a low score if generated from the model distribution PG. In contrast, D2 of X returns a high score for X generated from PG, whilst giving a low score for a sample drawn from P data. Unlike a standard GAN, the scores returned by the discriminators are real values rather than probabilities between 0 and 1. The generator G performs a similar role to that of a standard GAN, i.e., producing data mapped from a noise space to synthesize the real data. And then fool both two discriminators D1 and D2. All three players are parameterized by neural networks, wherein D1 and D2 do not share their parameters. More formally, D1, D2, and G now play the following three-player minimax optimization game. For J to increase, D1 of X must increase, and D1 of GZ must decrease. D2 of X must decrease, and D2 of GZ must increase. The authors introduced hyperparameters alpha and beta, which are greater than 0 and less than or equal to 1, to serve two purposes. The first is to stabilize the learning of the model. As the output values of two discriminators are positive and unbounded, D1 of GZ and D2 of X can become very large and have exponentially stronger impact on the optimization than log D1 of X and log D2 of GZ do. rendering the learning unstable. To overcome this issue, we can decrease alpha and beta, in effect making the optimization penalize D1 of G and D2 of X, thus helping to stabilize the learning. Instead of multiplying each log term by alpha and beta, we can also multiply each penalty term by the reciprocals of alpha and beta. Setting alpha and beta small increases the penalty, preventing D1 of GZ and D2 of X from becoming too large. The second purpose of introducing alpha and beta is to control the effect of KL and reverse KL divergences on the optimization problem. This will be discussed in the next page once we have the derivation of the optimal solution. Next, let's theoretically analyze the objective function of D2GAN. The minimax objective function of D2GAN is given as follows. As mentioned earlier, this expression contains two hyperparameters alpha and beta, which are greater than 0 and less than or equal to 1. This equation can be written as follows. Using the integral symbol, we express the expectation as follows. If we use the x from PG instead of the z from PZ, the second term can be written as follows. Since both g of z and x come from PG, g of z can be written as x. The same goes for the fourth term. Then the optimal discriminators D1 and D2 are as follows. To simplify notation, let D be P data and G be PG. Since D and G are both probability density functions of X, their integrals are each 1. Next, we substitute the D1 and D2 stars into the original loss function to find the optimal G. Then we can get this expression. Rearranging this, we get the following equation. This is the KL divergence between D and G, and this is the KL divergence between G and D. This is called forward KL divergence, and this is called reverse KL divergence. Since the first two terms are constants, we only need to minimize these two KL divergences. That is, training a D2GAN is equivalent to minimizing the forward and reverse KL divergences between two distributions P data and PG. This makes PG similar to P data and allows the generator to generate fake data that resembles real data. By fitting D1 to D1 star and D2 to D2 star, and finding the optimal solution G star for the generator G, we have the followings. In theory, for the optimal G with PG equal to P data, the KL divergences become 0. In this case, J star becomes this value. When alpha and beta are both 1.0, J star converges to -2. Also, if PG and P data are equal, then D1 star of X becomes alpha. And D2 star of X becomes beta for all X. This is given in Theorem 2 of Section 3.1 of the paper. We will verify this experimentally later when implementing the D2GAN model. Next, let's take a closer look at the hyperparameters alpha and beta. Let's first consider the forward KL divergence. Increasing alpha promotes the optimization towards minimizing the forward KL divergence. thus helping the generative distribution cover multiple modes, but may include potentially undesirable samples. Let's look at why. Let's assume that the two distributions PG and Pdata are as follows. Let's say that in this figure, the blue dots come from the distribution Pdata, and the red dots come from the distribution PG. And let's assume that PG is simpler than Pdata. In the interval where Pdata is 0, KL is already 0, so J is already minimized. We don't need to consider this case. However, in the interval where Pdata is greater than 0, PG must also be greater than 0 for KL to decrease. Otherwise, KL increases. Therefore, for KL to become smaller, PG must be as shown in the figure above. That is, as alpha increases, red dots appear in the area where Pdata becomes 0. In contrast, increasing beta encourages the minimization of the reverse KL divergence, hence enabling the generator capture a single mode better, but may miss many modes. In the interval where Pdata is 0, PG must also be 0 for the reverse KL to decrease. Therefore, for the reverse KL to become smaller, PG must be as shown in the figure above. That is, as beta increases, mode collapse occurs. By empirically adjusting these two hyperparameters, alpha and beta, we can balance the effect of two divergences, and hence effectively avoid the mode collapsing issue, as shown below. Now let's implement a D2GAN model in code. Generate a dataset consisting of 8 Gaussian distributions arranged in a circle like this. This code is very similar to the code we used before. Let's just look at the parts that have changed from before. We create 2 discriminator models, D1 and D2, and 1 generator model, G. Let's write a custom class to create the D2GAN model. The inputs to this class are D1, D2, G, and the hyperparameters alpha and beta. As with the previous code, we use the atom optimizer. Next, we write a function to compute the loss J of D2GAN using this formula, and write functions to compute the losses of the discriminators D1 and D2. Instead of maximizing the loss J, we will minimize the negative loss J. And we write a function to compute the loss of the generator G. The generator minimizes J, so we can just use J as is. In the train step method, we update the discriminators twice and the generator once. We create and compile the D2GAN model. We set both alpha and beta to 1.0. Next, let's write some code to check the results as we did before. Let's check the results. The losses of discriminators D1 and D2 measured during training are as follows. After 1,000 iterations, both losses converge to almost 2. Recall that we used -j to train D1 and D2. According to Theorem 2 discussed previously, after training D2GAN, the output of D1 becomes alpha, and the output of D2 becomes beta. Since alpha and beta are both set to 1.0, this becomes 2.0. For this reason, both losses of D1 and D2 converge to 2.0. This can also be verified by the following expression. The loss of G converges to -2.0. If we experimentally verify the outputs of D1 star of x and D2 star of x, we can see that they are each nearly 1.0. And the results of observing the distribution of fake data and real data during training are as follows. These results are similar to those of other GAN variants, such as unrolled GAN and Wasserstein GAN. Let's run this code. We got the following results. So far, we have looked at generative adversarial networks, GAN, through a total of 11 videos.